Dear student, warm welcome to NPTEL Phase 2 program video course on geosynthetics engineering in theory and practice. My name is Professor J. N. Mandal, Department of Civil Engineering, Indian Institute of Technology, Bombay, Mumbai, India. The name of the course Geosynthetics Engineering in Theory and Practice. This module 13, lecture number 62, Designing with Geofoam. I will now focus the recap of the previous lecture. This design of a magnet using geofoam, overturning due to the seismic effect, translation due to wind. Next, we are continuing with the testing of the geofoam material, that is apparent density test, water absorption test and compressive strength test. Now, I will address the proposed unconfined compression test PUCT on expanded polystyrene geofoam. There is no proper compressive state specification in India on expanded polystyrene geofoam. So, here we are just recommending this proposed compressive strength test on the expanded polystyrene geofoam, and the specimen size is shown here, that is the schematic diagram of the expanded polystyrene geofoam, and it is a kind of cylindrical shape geofoam and whose height is about 150 millimeter and diameter is 75 millimeter. Because you may be aware of the triaxial compression test of the soil. So, that looks like a cylindrical in shape and the ratio through the diameter to height about 2. So, here this diameter is considered about 75 millimeter and height is this double, that is 150 millimeter. So, this a type of the unconfined compression test is proposing on the EPS geofoam. The right hand side, that is B, that is the test specimen, and this is the red color, this is the expanded polystyrene geofoam which is cylindrical in shape, and also this specimen is kept between the two plates at the top and the bottom, and then you are applying the load from the top here, which is connected to the computer. So, here is the unconfined compression test on EPS geofoam with different densities. So, we have given the different color. This is A, that in density of geofoam is 15 kg per meter cube, and this B, that is density of EPS geofoam is 20 kg per meter cube, and this is the C, this is the C, and whose density of EPS geofoam 22 kg per meter cube, and D, the density of the EPS geofoam whose density is 30 kg per meter cube. So, we have taken that 4 different density of the EPS geofoam and have performed the compression test. So, from the test result you can obtain the stress strain relationship for the proposed unconfined compression test on the expanded polystyrene geofoam. Here this x axis is the strain in percentage and y axis is the compressive stress in kilopascal. So, you can see that initially this is the compressive stress is increasing with increasing the strain, and then you can see that strain is increasing, but with respect to the compressive strain it is not so as it was in the beginning. So, even then it is increasing. So, there is no decreasing kind of the trend is available here when you went up to even then 15% of strain. So, from this figure you can we observe that compressive stress value is increasing with increasing the density of the expanded polystyrene geofoam. Even then at a particular strain, minimum strain value, the compressive stress value is lying on almost at the same line. So, this compressive stress is very important to us. So, here we have performed the 4 different density of the sample. So, the density of EPS geofoam is 15 kg per meter cube, 20 kg per meter cube, 22 kg per meter cube and 30 kg per meter cube, and size of the specimen is the same for all cases, that is 75 millimeter in diameter and 150 millimeter in height. Now, most important that we have to determine what will be the compressive strain value in kilopascal at 5% strain and 10% strain, and also the yield value and the initial tangent modulus value in kilopascal. So, this value is important because we want to adopt for the design of any structure. So, for the 5% when the density of the EPS geofoam is 15 kg per meter cube, at the 5% this is 57.04 kilopascal, at the 10% compressive strength value is 62.92 kilopascal, and at the yield strength compressive strength value 52.89 kilopascal, and initial tangent modulus is 3395 kilopascal. When the density of EPS geofoam is 20 kg per meter cube and size of the sample is same, that is 75 millimeter diameter and 150 millimeter height, compressive strength at 5% strain is 85.33 kilopascal and 10% 93.03 kilopascal and yield 78.8 kilopascal. Initial tangent modulus 4074 kilopascal. Now, density of the EPS geofoam is 22 kg per meter cube and size of the sample is the same, 75 millimeter diameter and 150 millimeter in height, and compressive strength at 5% is 100.50 kilopascal and compressive strength at 10% is 106.16 kilopascal and yield value is 92.67 kilopascal and initial tangent modulus 5213 kilopascal. And at the end the density of EPS geofoam is 30 kg per meter cube, size of the specimen 75 millimeter diameter into 150 millimeter height, and compressive strength at 5% strain is 143.96 kilopascal. At 10% strain, compressive strength 150.07 kilopascal and at yield value is 123.56 kilopascal and initial tangent modulus 8149. You can observe that from this table that density is increasing, then compressive strength value also are increasing with increasing the strain, and also the yield value also are increasing, and initial tangent modulus value also are increasing. So, this value is important for the analysis. Now, here this figure show the relationship between the density of EPS geofoam rho and the compressive strength at 10% strain. So, this is the different density as we mentioned here 15, 20, 22 and 30. So, here for 15, 20, 22 and the 30. So, this is density of the EPS geofoam in the x axis, that is kg per meter cube, and compressive strength is kilopascal. So, we know that for this density 15, so what will be the compressive strength? So, we put this compressive strength value at 10% strain. So, 10% strain, suppose when it is 15 then 62.92. So, when it is 15 then 62.92. Like that, for when it is 20 then for at 10% strain 93.03. So, 93.03. Now, next when it is density is 22 at 10% strain 106.16. So, this is 106.16. When it is the density is 30, then at 10% strain that compressive strength value 150.07. So, this is 150.07. So, if we see here, you can draw a line which will give the straight line. So, from this relationship you can develop an equation for the compressive strength, that is sigma c will be equal to 5.799 into rho, that is density of the geofoam, minus 23.09, or R square is equal to 0.998. So, this equation also very important. If you know that what will be the density of the geofoam, so you can directly calculate that what will be the compressive strength of the EPS geofoam using this equation. And this equation also can be used for any analysis. Here the relationship between the density of EPS geofoam rho and the compressive strength at yield. So, this is the compressive strength at yield. So, we know that this is the x axis is the density of the EPS geofoam kg per meter cube, y axis is the compressive strength in kilopascal. So, we know for the different density either 15, 20, 22 and the 30, we know what is the compressive strength at yield, that means this value compressive strength at yield. So, if you substitute this value, so you can have a linear equation like this, and then you can develop that what will be the compressive strength at yield, that even then if we say sigma c will be equal to 4.689 rho minus 15.01, R square is equal to 0.988. So, from this equation also you can calculate what will be the compressive strength at yield. So, if you know that what will be the density of the expanded polystyrene geofoam, so you can calculate compressive strength at yield. Now, this is compressive strength test result as per different test specification. We have performed in our geosynthetics testing research and testing laboratory, and for all the different density of the EPS geofoam and the different method. You can see as per STM D162110, IS 46711984, DIN 534211984 and PUCT IIT Bombay, this is the proposed. So, you can see that for different density that what will be the compressive strength at 5% and 10% for all specification. You can see as per ASTM this is 54.8, then at when it is density is 20 is 81.6, when density is 22 then compressive strength value is 92.4, and when density is 30 this is 128.20. At 10% when the density is 15 this value compressive strength value 59.6, when density is 20 this compressive strength value 88.4, and when it is 22 this is 108.2, and when density is 30 this is 142.7. And this 5% and 10% represent the compressive strength value of EPS geofoam, which has been calculated at 5 and 10% of axial compression stress of the specimen. And this is the PUCT IIT Bombay, that is the proposed uniaxial compression strength value. If you can see at the 5% strain it gives 57.04 when the density is 15 kg per meter cube. When density is 20 kg per meter cube then compressive strength value at 5% is 85.33, and when it is 22 this is 100.50. When it is 30 kg per meter cube density then compressive strength value 143.96. Whereas in case of the 10% when density is 15 kg per meter cube compressive strength value 62.92, and when it is density is 20 kg per meter cube this compressive strength value 93.03. When density is 22 kg per meter cube this at 10% compressive strength value 106.16, and when that density is 30 kg per meter cube at 10% 150.07. Now if you can compare with the ASTM and the proposed that uniaxial compressive strength, you can see that variation in the result. This is 54.8, whereas this is 57.04, this is 81.6 at 5% strain, this is 85.33, this is 92.4 at 5%, this is about 100.50, this is 128.20, and this is 143.96. Similarly, at the 10%, this is 59.6 for 15 density, whereas this gives 62.92 compressive strength. Then this is 88.4 at 20 kg per meter cube density, then this proposed is given 93.03. So at 22 density 108.2 at 10%, and they are at 10% 106.16. So at 30 density 142.7, and this proposed is giving 150.07. Even then if you compare with the STM it is reasonably will match. So we can recommend this kind of the testing for the compressive strength. Even then you can compare with the other method at 5% and the 10%, you can have something variation, not so variation, but some variation in result. Also in the DIN also you can see that there is some variation in result. So it is much more the appropriate this result which is matching with the ASTM and this proposed method. And it is also that very easy to produce a geofoam material like cylindrical in shape, and if you have any machine, compressive strengthening machine, even then triaxial machine, you can perform easily. You don't require any additional kind of the equipment to perform this compressive strength value. So it is easy to perform the test, and it is easy to produce this cylindrical geofoam material. And this will be the more appropriate method to calculate this compressive strength of the expanded polystyrene geofoam. Now, we will discuss the tensile properties of geofoam as per STM D162309. The objective of this test to determine the tensile strength properties of the geofoam. And here the test specimen type A, that is recommended type A test specimen with its dimension as shown here. You can see here very typical tensile stress specimen of geofoam of density is 15 kg per meter cube, this is 20 kg per meter cube, this is 22 kg per meter cube, and this is 30 kg per meter cube. Here I am showing that what should be the sample, and this is the all dimension is given in millimeter. This to this is about 108 millimeter, and from here to here is about 55.5 millimeter, and this here to here is 41.5 millimeter, this also 41.5 millimeter, and this to this is about 25 millimeter, and this angle is 18 degree. So, it is like a dumbbell shape. This also is 28.7, this is the diameter here 28.7, and this also 55.3. So, it is a like a dumbbell shape, and sometimes also is very difficult to manufacture or to produce this kind of dumbbell shape for the determination of the tensile strength of the expanded polystyrene geofoam. So, we have also fabricated the gripping assembly for this. It is also very complex. You can see this is the jaw. We have also fabricated and developed, and this is the box, and here is the tensile strength test setup on the expanded polystyrene geofoam material. This is a kind of, I say that like this dumbbell kind of the shape, and which you are to be grip at the top and the bottom, and this is the what you call the gauge length. And this is the test before the test, and you can see that after the test, and this is very typical failure. You can see here is the typical failure almost at the middle of this portion. So, the failure pattern is here. So, this is tensile strength before the test and after the test. So, for all densities we have performed, and this is the fail specimen in tension. You can see very typical failure. Okay. So, this is very important also parameter. This is here is showing that 4 density, that is 15, 20, 22 and 30 kg per meter cube. This is the before the test, and you can see this is the after the test, that how the sample fell. So, you have to calculate from this tensile strength that what will be the tensile strength is calculated by dividing the breaking load by the original minimum cross sectional area of the specimen. So, tensile strength sigma t is equal to F divided by pi into d square by 4. So, that means F is the tensile force applied to the specimen is kilonewton, and d is the minimum diameter of the test specimen in meter. So, considering the density of the expanded polystyrene geofoam is 20 kg per meter cube, let us consider that we are calculating only for the density of 20 kg per meter cube. So, tensile stress will be equal to breaking load by cross sectional area, and breaking load is 0.14, this divided by cross sectional area pi into 0.0287 square divided by 4, that will give the tensile stress value 216.40 kilo Pascal. Now, this is the stress strain behavior of the expanded polystyrene geofoam in tension. So, this is x axis is give the deformation is millimeter and this is the tensile load in kilonewton. You can see the nature of the curve is like this. That means the tensile load is increasing with increasing the deformation, and this is shown only for the density of expanded geofoam is 20 kg per meter cube. So, when the deformation is about 4.7 millimeter, then the tensile load is 140 Newton. Now, this is the test result for the tensile strength of expanded polystyrene geofoam for various density. When the density of EPS geofoam is 15 kg per meter cube, and this is as per STM D162309, the tensile strength value is 154.89 kilopascal and strain at failure is 2.56%. When the density of EPS geofoam is 20 kg per meter cube, the tensile strength value is 216.40 kilopascal and strain at failure 2.71%. When the density of EPS geofoam is 22 kg per meter cube, the tensile strength is 244.54 kilopascal and strain at failure 2.74%. When the density of EPS geofoam is 30 kg per meter cube, the tensile strength is 407.78 kilopascal and strain at failure 2.82%. So, if observe that the density is increasing, then the tensile strength value also is increasing and the strain value also is increasing. So, if the tensile strength value is from about 154.89 to 407.78 kilopascal depending on the density of the expanded polystyrene geofoam. Also the strain value which is lying between 2.56% to 2.82%. Now, correlation between the tensile strength and the density of the expanded polystyrene geofoam. So, here is the x axis is density of the EPS geofoam is kg per meter cube and y axis is the tensile strength in kilopascal. For the different density, you know what will be the tensile strength value. So, for 15 you know what will be the tensile load, similarly for 20, 22 and then 30. So, then you can have a linear line like this and you can establish a equation which is sigma t is equal to 17.14 rho minus 116.9 or R square is 0.981. So, from this equation also you can directly determine what will be the tensile strength of the geofoam if you know that what will be the density of the geofoam. If the rho is known, then you can calculate what will be the tensile strength of the geofoam from this equation. Now, as you have observed that tensile strength of the expanded polystyrene geofoam by the STM method is quite complex, because it is sometimes very difficult to produce the dumbbell shape of the specimen, and as well as you also require typical clamping arrangement or jaw arrangement for this to hold this specimen into this machine. So, we have recommended and proposed the test specimen for the tensile strength of the geofoam. So, in this proposed tensile strength test, this test specimen has thickness of 25 millimeter with a flat section. This figure shows that schematic representation of the test specimen. You can see that here we have performed with the different density and also different shape and size and also the different thickness, and then we have come to a conclusion that this kind of the thickness will be the much more appropriate. And here I am showing you that detailed dimension of this I shape, this expanded polystyrene geofoam specimen. here this is 250 this millimeter and this is 170 millimeter and this one is 140 millimeter, this is 150 millimeter, this is 75 millimeter and this is about your 90 R. Okay, this is 25 R here and this to this is about 500 millimeter and this to this here is 25 millimeter. So, you can, if you have, because you can very easy to make the sample, because you can have the different thickness of the expanded polystyrene geofoam and then you can simply cut with this dimension. So, it is very easy to prepare this kind of the geofoam sample. So, it is easy to cut and easy to prepare. It is not a dumbbell shape or there is a complex and also it is very easy to clamp at the both end of this sample. So, we have this developed this kind of the gripping assembly. You can see this is the gripping, this assemble for the tensile strength of the expanded polystyrene geofoam and this is the different tensile strength test specimen whose density of the geofoam material are from this is 15 kg per meter cube, this is 20 kg per meter cube, this is 22 kg per meter cube and this is 30 kg per meter cube. So, this is the testing sample with different density and this is the gripping assembly. So, here we are performing that tensile test on the expanded polystyrene geofoam. So, here it is a clamping. You can see clamping is very easy with this kind of the specimen and this is, you can see this extension form, here it is, this is the sample of geofoam white in color and before the test and after test you can see this is a kind of the failure, this is a kind of very typical failure of the geofoam in a for the tensile test. So, here is the different sample, different density before the test and here you can see after the test from the different density. So, now we have obtained the tensile stress strain behavior of expanded geofoam material. This is x axis is the strain value and y the tensile stress in kilopascal. This is for 15 kg per meter cube, the density of the EPS geofoam and next red one is the 20 kg per meter cube, then green again the 22 kg per meter cube and then this is 30 kg per meter cube. You can see here that the strain increasing tensile stress value also are increasing in all cases and in all cases this density of the EPS geofoam is increasing with increasing the tensile stress of the EPS geofoam and this all cases almost this strain value is lying below the even then 3% of strain. So, here is the table which shows the tensile strain test result and then comparison with the ASTM D162309. Because this we are proposing because it is very easy to produce this kind of the product and very easy for the gripping arrangement and very easy to perform the test. So, here density of EPS geofoam is 15 kg per meter cube as per ASTM D162309, tensile strength is 154.9 kilopascal and strain at failure is 2.56%. Whereas in the proposed tensile strength at IIT Bombay, the tensile strength is 154.13 and strain at failure 2.23. You can see that lot of similarity is there with the STM and the proposed tensile strength method, and this test is recommended for use in India. So, density of the EPS geofoam is 20 kg per meter cube. The tensile strength is 216.40 kilopascal. The strain at failure is 2.71%. And this proposed tensile strength is ITB is 216.16 kilopascal and strain at failure 2.62%. So, density of EPS geofoam is 22 kg per meter cube. The tensile strength value 244.54 kilopascal and strain at failure 2.74%. And the proposed method tensile strength value is 246.88 kilopascal and strain at failure 2.63%. When the density of the EPS geofoam is 30 kg per meter cube, as per STM, tensile strength is 407.78 and the strain at failure is 2.82%. Whereas that proposed method tensile strength is 411.56 kilopascal and strain at failure 2.74. So, you can see that lot of similarity of the value of the tensile strain and the corresponding the strain value has been obtained. So, tensile strength value for the STM is lies between 154.89 to 407.78 kilopascal, whereas this proposed method this tensile strength value lies between 154.13 to 411.56 kilopascal. So, depending upon the density of the EPS geofoam, so there is a quite good agreement between the tensile strain and also the corresponding the strain value. So, strain at failure as per the STM is 2.56% to 2.82%, whereas this proposed method is 2.23% to 2.74%. So, it is well agreement with the STM method and proposed method. So, we recommend that proposed method is much more though simpler and easy to manufacture and easy to test, because different types of the thickness of the expanded polystyrene geofoam is available. So, you can cut the proper size and the shape which we have optimized, and we come up with the proper specification and which is matching as per the STM test specification is concerned. So, this will be very useful and recommended for the tensile strength of the EPS geofoam. So, next we will talk the shear properties of the geofoam. This is STM C273 C273M-07A. Now, objective of this test to determine the shear strength parameter of the geofoam. This is also very important because the geofoam material has to placed with other kind of the material, and you should know that what will be the shear strength properties of the geofoam material. So, test specimen also shall be the 300 millimeter into 50 millimeter into 25 millimeter. So, here is the schematic representation of the sample of geofoam. This is the 300 millimeter and this is 50 millimeter and this is 25 millimeter. You can see the right hand side, this is the shear strength test specimen with the different density. This is 15 kg per meter cube and this is 20 kg per meter cube, this is 22 kg per meter cube and this is 30 kg per meter cube. With different color has been given because to identify this what density you are using in the geofoam, because this all the geofoam is white in color, sometimes it is difficult to identify that what will be their density. So, that is why when we are performing the test and we have been provided with the different color to identify like that geogrid has a different strength. So, some for identification, some of the manufacturer had provided with some kind of the color, yellow color, green color, like a thread to identify for the worker that what is the strength of the geogrid material. Similarly, here this color has been given to identify that what will be the density of the EPS geofoam material. So, this is the shear stress assembly for the expanded geofoam material, and this is the shear strength test of the EPS geofoam. You can see here this have been fabricated in our geosynthetics testing and research laboratory. This is the plate shear, this specimen, this is the plate here, and this is the geofoam material specimen is here, and this is the steel plate, this is the steel plate, this is the steel plate, and this is moving this direction, this is moving this direction. So, there is a development of the shear between the geofoam and the steel. So, which you can see here. So, here it is for different density, this A for 15 kg per meter cube, this for B 20 kg per meter cube, this is C 22 kg per meter cube, and D 30 kg per meter cube. So, this test has been performed. So, from this test you have to calculate what will be the shear stress, that means tau of the geofoam material. So, tau is equal to P divided by L into B, where tau is equal to core shear stress in kilopascal, and P is instantaneous force on specimen, that is in Newton. L is equal to length of the specimen in meter, and B is width of the specimen in meter. So, maximum shear stress tau max can be defined, tau max is equal to P divided by L into B. So, now considering the density of the EPS geofoam 20 kg per meter cube. So, we have only shown for the one density, similarly we can calculate for the other densities also. So, for 20 kg per meter cube of density, P value is giving 1.412 kilonewton, and L length is 0.3 meter, and B is 0.05 meter. So, tau max will be equal to 1.412 divided by 0.3 into 0.05 will give 94.37 kilopascal. So, shear stress strain gamma of the geofoam material also can be determined, that gamma is equal to U by T, where U is equal to deformation at peak shear load, that is in millimeter, and T is the thickness of the core, that is in millimeter. So, this gamma value we are having that 4.67 millimeter, this divided by thickness of the core in millimeter is, this is 2.5. So, this will give 25. So, this will give you 0.1868 millimeter per millimeter. So, this is the shear strain of the geofoam material. Now, core shear modulus, that is capital G of the geofoam material. So, G is equal to delta P by delta U into T divided by L into B, where delta P by delta U is equal to slope of the force displacement curve, that is Newton per millimeter, from 0.002 millimeter per millimeter to 0.006 millimeter per millimeter effective engineering shear strain. Now, delta P by delta U, you can obtain 855.88, and T is equal to 0.025 meter, L is 0.3 meter, and B is 0.05 meter. You know the size of the sample, length, width, and breadth. So, from this you can calculate what will be the shear modulus G. So, G will be equal to delta P by delta U is 855.88 into the T is 0.025. This divided by L is equal to 3 meter into that B is equal to 0.05 meter. So, this will give G value, that means shear modulus value of geofoam is 1426.467 kilopascal. So, here is the shear strain test result for density of the EPH geofoam, then the maximum load at failure, what is the shear strength in kilopascal, deformation at peak load is millimeter, delta P by delta U, which you can obtain from the graph, and core shear modulus in kilopascal. When density of EPH geofoam is 15 kg per meter cube, maximum load at failure 1255 Newton, shear strength 83.65 kilopascal, deformation at peak load is 5.62 millimeter, and delta P by delta U is 668.18, which you can obtain from the graph, and the core shear modulus is 1113.633 kilopascal. When the density of the EPH geofoam is 20 kg per meter cube, maximum load at failure 1416 Newton, shear strength is 94.37 kilopascal, deformation at peak load is 4.67 millimeter, and delta P by delta U is equal to 855.88, and core shear modulus value 1426.467 kilopascal. When density of the EPH geofoam 22 kg per meter cube, the maximum load at failure 1823 Newton, and shear strength value is 121.57 kilopascal, and deformation on peak load 4.31 millimeter, and delta P by delta U is 902.36, and core shear modulus 1503.933 kilopascal. When the density of EPH geofoam is 30 kg per meter cube, the maximum load at failure 2089 Newton, the shear strength value 139.27 kilopascal, and deformation at peak load 2.67, and delta P by delta U 1130.9, and core shear modulus 1884.833 kilopascal. You can see from this table that shear strength value is lying between 83.65 to 139.27. That means density is increasing, the shear strength value also are increasing. Now, breaking load and fractional properties of the geofoam as per STM C20305A. Now, objective of this test to determine the breaking load and the fractional properties of the geofoam. This is also very important parameter. So, this method available is the 3-point method and the 4-point method. Here you can see this is the 3-point method and this is the 4-point method here. So, this is the beam and which dimension also is given, and you can perform the test, that fractional strength test method, and then you can calculate what will be the fractional strength of the geofoam material. So, here is the test specimen. Here is the test specimen, and this test specimen, that size is about 300 millimeter, and this is the 100 millimeter, and this is the 25 millimeter. And this is the fractional strength test specimen of density of the geofoam material. This is 15 kg per meter cube, this one is 20 kg per meter cube, this is 22 kg per meter cube, and this is 30 kg per meter cube. So, these are the different densities of the expanded polystyrene geofoam material. Now, this is the fractional test assembly has been developed and fabricated in our laboratory. So, this is the fractional test assembly of geofoam. Span length is 250, whereas you can see that geofoam specimen sample is 300 millimeter. So, that 300 millimeter also can be rest on this on on this geofoam assembly. You can see that different type of densities of the material before the test. So, this is fractional strain test on the geofoam, this is the before the test. Okay. And then you can look that after the test, this for density is 15 kg per meter cube, this is 20 kg per meter cube, and this is 22 kg per meter cube, and this is 32 kg per meter cube. This is like a bending, you can see, and this all are typical nature of the failure of expanded polystyrene geofoam material during the fractional test. So, here we can also observe the EPS geofoam specimen after failure, very typical failure of the expanded polystyrene geofoam for different density. Now, here is the fractional strain test result. When the density of the EPS geofoam is 15 kg per meter cube, this is as per STM C20205. So, fractional strength value 149.9 kilopascal and deformation is 25.41 millimeter. When the density is 20 kg per meter cube, the fractional strength 211.3 kilopascal and deformation is 33.13 millimeter. When density is 22 kg per meter cube, the fractional strength 240.6 kilopascal and deformation is 38.11 millimeter. When the density is 30 kg per meter cube, fractional strength 277 kilopascal and deformation 46.07. So, from this table also it has been observed that the fractional strength also are increasing with increasing the density. So, it lies between 149.9 to 277 kilopascal. And also deformation also equally are increasing with increasing the density of the expanded polystyrene geofoam that lies between 25.41 millimeter to 46.07 millimeter. So, maximum fiber stress S can be determined using this equation. S is equal to 3 into PL by 2 B d square. S is equal to stress in the outer fiber, that is in kilopascal. P is equal to load at given point on the load deflection curve in Newton. L is equal to support span in meter, and B is equal to width of the beam tested in meter, and D is equal to depth of the beam tested in meter. Now, considering the density of the EPS geofoam 20 kg per meter cube, where P is equal to 0.0342 kilonewton, L is equal to 0.25 meter, and B is equal to 0.1 meter, and D is equal to 0.025 meter. So, fractional strength can be defined 3 PL divided by 2 B d square. So, fractional strength is equal to 3 into P is 0.0342, this into L value is 0.25, this divided by 2 into B value is 0.1 and D value is 0.025 square. So, this will give the fractional strain value 211.3 kilopascal, which I have shown you earlier this value. Maximum strain value epsilon, the maximum strain in the outer fiber occur at the mid span. So, epsilon is equal to 6 capital D into small d by L square, where epsilon is equal to maximum strain in the outer fiber, that is millimeter by millimeter, and capital D is equal to maximum deflection of the center of the beam, that is in millimeter, and L is support span is millimeter and D is depth is millimeter. Here D, capital D is equal to 0.03313 meter and small d is equal to 0.025 meter and L is equal to 0.25 meter. Now, maximum strain epsilon can be, we can substitute value, that 6 into D, D is 0.03313 into small d, this is small d 0.025, this divided by L square 0.25 square. So, this will give the maximum strain value 0.08 millimeter per millimeter. So, you can calculate that what will be the maximum strain. Also, you can calculate that moment of inertia. The moment of inertia is calculated as follow: I is equal to B d to the power q by 12, where I is equal to moment of inertia, that is millimeter to the power 4, and B is equal to specimen width is millimeter, and small d is specimen thickness is millimeter. Here B is given 0.1 meter and D is equal to 0.025 meter. So, I, that is moment of inertia, will be equal to, this is B, B value is 0.1, and this is D, D value is 0.025 to the power q, this divided by 12, which give the moment of inertia value 1.3 into 10 to the power minus 7 meter to the power 4. So, you can calculate that what will be the moment of inertia of the expanded polystyrene geofoam. Elastic modulus of the geofoam material can be given as E is equal to 1 by 48 P L to the power q divided by I into D, where E is equal to elastic modulus in kilopascal and capital D is the corrected deflection at center of the sample in meter, I is equal to moment of inertia meter to the power 4, capital L is equal to support span, that is in meter, and P is load at a given deformation within the proportional limit of the specimen, that is kilonewton. Here P is equal to 0.0342 kilonewton, capital L is equal to 0.25 meter, I is equal to 1.3 into 10 to the power minus 7 meter to the power 4, and capital D is 0.03313 meter. Now, you substitute this value into this equation. E is equal to I is equal to 1.3, this is 1 by 48, sorry, P is equal to 0.0342 into L is 0.25 to the power q, this divided by 48 into I, this is I is equal to 1.3 into 10 to the power minus 7 into D, that is D is equal to 0.03313. So, this will give you that what will be the elastic modulus of the geofoam, this is 2584.87 kilopascal. Now, this is the fractional strength test result, that is density of the EPS geofoam, then maximum load at the failure, fractional strength in kilopascal, deformation at the center in meter, and maximum strain as millimeter per meter, and moment of inertia m to the power 4 and modulus of elasticity in kilopascal. When the density of EPS geofoam is 15 kg per meter cube, maximum load at failure is 0.025 kilonewton, fractional strength 149.9 kilopascal, and the deformation 0.02541 meter, and the maximum strain at millimeter per millimeter 0.06, and moment of inertia 1.3 into 10 to the power minus 7 m to the power 4. Modulus of elasticity 2518.69 kilopascal. When density of EPS geofoam 20 kg per meter cube, the maximum load at failure 0.0342 kilonewton and fractional strength 211.3 kilopascal, and the deformation at the center is 0.03313 meter, and the maximum strain millimeter per millimeter is 0.08, and the moment of inertia 1.3 into 10 to the power minus 7 m to the power 4, and the modulus of elasticity 2584.87 kilopascal. When the density of the EPS geofoam is 22 kg per meter cube, maximum load at failure 0.0401 kilonewton, the fractional strength is 240.6 kilopascal, and deformation at center is 0.03811 meter, and the maximum strain 0.09, and the moment of inertia 1.3 into 10 to the power minus 7 meter 4, and modulus of elasticity 2815.95 kilopascal. When density of the EPS geofoam is 30 kg per meter cube, the maximum load at failure 0.0461 kilonewton, fractional strength 277.0 kilopascal, deformation at center 0.04687 meter, and the maximum strain is 0.11, and moment of inertia 1.3 into 10 to the power minus 7, and modulus of elasticity 3088.52 kilopascal. So, you can have that different values of the maximum load at failure, what will be their fractional strain, deformation and the strain, and also you can calculate the moment of inertia and modulus of elasticity of expanded polystyrene geofoam material. So, these are the properties, these are the data, all these data in the fractional strength is very important to our various problem in geotechnical or civil engineering. So, these are the mainly that some of the tests we have covered in these courses. With this, I just finish my lecture today. Please let us hear from you any question. Thanks for hearing.